Good afternoon, everyone, and thank you very much for joining us today. My name is Sagar Desarda, and I'm America's tech leader for Edge Networking Services. I have Blake Thompson co-presenting with me today, and I'll let him introduce himself.
So hi, I'm obviously Blake Thompson. I'm the director of Maps API at Mapbox. So I'm really excited to be here and talk with you all a little about how we use CloudFront. So go ahead.
Thanks, Blake. So maintaining a good website performance is critical to online businesses. The performance influences your SEO, your brand credibility, it improves conversion rates, and of course, the user experience. And this is why we care about web performance. Today, we're going to talk about how Amazon CloudFront makes your web applications fast, including reducing your overall page load time and improving the perceived user experience. And a quick level set that this is a 300 level session. So I assume that you have a good foundational understanding with the edge networking services such as CloudFront, Route 53, etc. Our agenda for today is I'll talk about AWS global infrastructure that AWS provides Mapbox to build their applications on, something that they find a lot of value in. AWS has built one of the world's largest physical global networks. Today, it reliably is carrying exabytes of business-critical customer data around the globe every second. And this year, we are opening up about some of the work that we do behind the scenes, and I'm very excited to share some of that with you all. Blake will then talk about how Amazon CloudFront enables Mapbox to power navigation as they provide global maps, real-time traffic, location search data, and so much more. And all of that is happening on AWS today. I'll then talk about running your compute at the edge, where you can deploy the code, and it'll run globally on the CloudFront edge locations, giving you exceptional performance, and you do not have to worry about managing the servers or the infrastructure underneath. Lastly, I plan to share some of the recent feature launches on Amazon CloudFront. 90 to 95% of our product roadmap is determined by our customer feedback. And this year, we've delivered on a lot of things that you all have been asking for, and I'm excited to share and talk to that. The AWS network provides customers with the most reliable and secure global infrastructure with access to virtually unlimited capacity without trading off performance. AWS has been recognized as the leader in cloud infrastructure services for 11 years in a row in Gartner's Infrastructure as a Service Magic Quadrant. We have reinvented the cloud network, establishing virtually unlimited network capacity so that you can run all of your data-intensive applications on AWS. And with this virtually unlimited capacity, the AWS cloud network is ready for multiple times projected peak customer usage and therefore does not have to tier or prioritize some customer traffic over others. All the 30 AWS regions, 95 availability zones, and over 410 edge locations, they're all interconnected via our low latency private network infrastructure via the transoceanic cables across the Atlantic, Pacific, and the Indian Oceans, as well as the Mediterranean Sea, the Red Sea, and the South China Sea. The CloudFront edge locations are connected to the AWS region through this AWS backbone network, which is fully redundant. It has multiple 100 gigabit Ethernet private fiber links that circles the globe with links with tens of thousands of networks for improved origin fetches and dynamic content acceleration. AWS is a global leader in deploying 400G and has taken this deployment as an opportunity to re-image how the cloud networks are built and improving capacity and reliability at every layer of our physical network build. AWS owns and operates its networking infrastructure, the optics, the switches, the racks, the servers, and supply chain, obsessing over designing and deploying custom hardware to reduce the complexity and points of failure. AWS uses custom-built networking hardware, such as switches and optical modules, enabling more granular monitoring and efficient capacity scaling than what is achievable with the market devices today. With millions of devices, each providing hundreds of data points every second, AWS analyzes trillions of data, correlating, discovering, and solving reliability issues that were previously unknown. To improve the reliability beyond what is available with the vendor hardware, AWS has custom-designed new cloud-optimized switches, reducing failure rates by 80% over the leading vendor devices. All the data flowing across the AWS global network that interconnects our data centers and the regions is automatically encrypted at the physical layer before it leaves our secure facilities. Additionally, AWS optics protect your data using advanced tamper detection such as laser security to automatically shut down and reroute connections if the network links are disturbed. AWS maintains full chain of custody through the entire manufacturing supply chain for all the hardware parts that are deployed on the AWS network, allowing us to identify and resolve any attempted hardware attacks. AWS writes the software for all the network devices and owns all the patch updates, ensuring that the code is verified, removing the reliance on vendors. This also enables us to run fleet-wide updates multiple times per month. Any internet traffic that moves onto the AWS network is scrubbed by AWS Shield, mitigating more than 10,000 DDoS attacks per month, with over 99% of those attacks are automatically resolved, and the remaining attacks are remediated by our 24/7 response team. When you use AWS Shield Standard with Amazon CloudFront and Route 53, you receive comprehensive availability protection against all known infrastructure attacks at the network layer and the transport layer. For advanced application-level DDoS support, customers can work directly with the same experts that protect the AWS infrastructure and Amazon.com to identify and remediate the attacks using AWS Shield Standard. AWS monitors the AWS network and public internet routes, diagnosing issues rapidly and automatically optimizing the traffic to avoid congestion and outages before customer applications are impacted. AWS consumes billions of networking probe measurements across thousands of service provider paths every day to map a global view of AWS client internet reachability and performance. The AWS network is massive, with a fleet of over 1 million network switches connecting exabytes per second of capacity available to our customers. AWS uses automation, which monitors our network and public internet routes, diagnosing issues rapidly and making over 3 million changes a week to optimize the traffic, avoiding congestion and outages before our customer applications are impacted. And because of this intelligent automation that we have built in, we are able to run without a network operations center or a NOC, which many networks need to run 24/7 to identify networking issues and remediate them manually. And this redesigned AWS networking fabric enables a one-size-fits-all deployment model and allows the same connections and networking hardware to be used to scale faster than ever before. It is now easier for us than ever to add capacity and new services at existing locations. And because of this, in the last year, AWS deployed more networking capacity into the AWS edge locations than the first 15 years of AWS combined. And we have tripled our overall network capacity over the last 3 years. With Amazon CloudFront, AWS operates the largest global content delivery network, or the CDN, of all the cloud providers, which enables our customers to securely deliver their data, videos, applications, and APIs to their end users with low latency and high transfer speeds. The edge is now the new frontier for innovation as enterprises accelerate their business transformation efforts with hybrid architectures. Provisioning network services at the edge improves global web application performance and secures corporate networks, applications, and devices. You can integrate AWS Web Application Firewall with Amazon CloudFront to keep your applications and APIs secure. Amazon CloudFront peers with thousands of telecom carriers globally and is well connected with all major access networks for optimal performance. We reduce the latency by delivering the data through more than 450 edge locations with automated network mapping and intelligent routing. I'm now going to have Blake talk about Mapbox's journey and their experience building their applications on Amazon CloudFront.
Oh, sorry. Thanks, Sagar. It's a pleasure to be here. So in my time at Mapbox, I've led multiple teams to build high throughput and low latency architectures on AWS. Our services have gone through many incremental steps over the time, and as we've grown to over 1 trillion requests a year, in doing so, we've focused a lot over time on how we can better leverage CloudFront to make our applications even better as we continue to grow. And I'm excited to share that today. From the moment we wake up, accurate and readily available location information is essential to everything we do. Think about it. Check the weather, you need to know the location. Get directions to a meeting, location. Order food, location. Location intelligence is critical to how we live, work, and innovate in the digital age. Maps and location are a part of everything. At Mapbox, we are building the platform to let developers own this experience, to design apps and put locations into the applications that you are building. Our tools let you customize everything: style, look and feel of the maps, to controlling the underlying data. The developers who build the apps and services we depend on require a fast and accurate location service to make our lives run smoothly and happily. These developers build with Mapbox. Most people in the room here should be using at least 3 services powered by Mapbox today. It could be a news article, a package delivered to your doorstep, or a search for your dream home. The performance and reliability of Mapbox's API are critical to the location experiences in your day. Mapbox customers right now make more than 4 billion deliveries annually. That's more than 500,000 every hour. At Mapbox, the operational excellence of our application is the highest priority. We build applications knowing every millisecond, kilobyte, and failure can greatly impact our customers. If you are navigating a vehicle using Mapbox navigation applications, a slow response or a failed request can ruin your day and the entire experience. If this happens, it might take you longer to get home, or that package may not be delivered to your doorstep. This is where we leverage CloudFront to provide that content acceleration, push the data closer to our end users so that we're able to deliver them an amazing experience with our services. To build a great application for our customers, these are the 4 pillars we build our performance strategy around. We must always be available, everywhere around the world, no matter the shifting traffic patterns of traffic on our application. If there's a typhoon in Japan or a breaking news story, a map can often provide the best context to tell a story. As a result, we can experience traffic surges from almost anywhere in the world at any time. CloudFront protects us at our origin servers with its scale and good cache offload that we maintain, making sure that we remain available. Similarly, we must have amazing performance. Think about when you're painting around on an interactive map. The responsiveness of that map is critical to your experience. CloudFront helps us keep data close to our users, allowing us to deliver fast and personalized experiences on any device anywhere. We are leveraging serverless functions on CloudFront to do more work on the edge. It allows us to reduce the complexity of our origin code and build globally distributed applications at scale. Finally, we have to constantly measure and understand our services. Information out of CloudFront powers a massive monitoring and business intelligence stack at Mapbox, helping us understand if our customers are having a good or a bad day. And if they're having a bad day, we can respond accordingly. So, how do you avoid application availability issues? How do you mature your application as you scale to meet the growing demands of your customers? Well, Mapbox has origins in over 8 AWS regions behind our CloudFront distribution, all of them actively serving traffic. We strategically place our origins globally to maintain the low latency. And we use Route 53 to customize different routing strategies between those regions based on the application. And CloudFront powers multiple Mapbox applications. We tweak our CloudFront configurations consistently to make incremental improvements, and over the years, we've learned a lot. With that in mind, I wanted to share some of the recommendations on how you can improve your application performance with CloudFront. Cache policies are simple but powerful. I would highly recommend identifying opportunities to utilize them to improve your cache offload and thus improving your availability. With CloudFront cache policies, you can cache and serve the same dynamically generated pages to different end users. The cache key is the unique identifier for every object in the cache, and it determines whether end users results in a cache hit or not. With a CloudFront cache policy, you can specify the HTTP headers, cookies, and query strings for the CloudFront to include in the cache key. As an example, say we are caching location data on a URL. We want to fork the cache by country and a postal code. We also want to exclude certain web analytics parameters so they don't fork the cache. And include certain cookies as part of the cache key, since they influence the response to the request. This is how we can build a flexible cache key for your dynamic content on CloudFront. So cache policies help us increase our cache offload, but at Mapbox, our global data sets are constantly being updated. And because of that, we want to get the end user to get the most accurate information. When our SDKs run an update, our API services respond with a delta between the latest version and the SDK's version. Then the SDK rebuilds the latest version with the delta. We use eTag validation by sending the if-none match headers sent from our SDKs. And if the content hasn't changed, the origin or the CloudFront cache will just respond with an HTTP 304. Doing so allows us to reduce the total amount of data downloaded by our client. Today, I'm happy to share that over 40% of our requests on our Maps APIs result in HTTP 304s. To further conserve bandwidth usage, the Mapbox SDK makes a lot of byte range requests. Imagine a customer is driving while downloading a larger set of map data, and they suddenly lose connection as they drive through a tunnel. Since our SDK makes byte range requests, the download resumes once the connectivity is reestablished. This helps our application to remain highly available and performant, even when the network is spotty. By incorporating these optimizations with CloudFront, we were able to reduce the download restarts by 5%, thus improving all of our end users' experiences. So, the use of CloudFront, the use of cache policies, if-none match, and byte range requests have certainly helped us reduce the hits to our origin, but we still can have a problem. We run frequent map updates. When that happens, CloudFront does absorb the volume of requests with the high cache offload that we have. But we still see a large number of simultaneous requests simultaneous requests to the origin for the same object. And this is where Origin Shield helps us. Origin Shield acts as an additional layer of caching in front of the origin to further improve the cache offload and protect the origin's availability. It can further reduce the number of simultaneous requests for the same object that are sent to your origin. Requests for content that is not in Origin Shield's cache are consolidated with other requests for the same object. This can result in as few as one request going to your origin. Also, when you enable Origin Shield in the AWS region that has the lowest latency to your origin, you can get much better network performance. For origins in an AWS region, CloudFront network traffic remains on the high throughput CloudFront network all the way to your origin. For origins outside of AWS, CloudFront network traffic remains on the CloudFront network all the way to the Origin Shield, which has a low latency connection to your origin. You heard me speak about Mapbox Mapbox's origin set up being globally distributed. We use Route 53 as our DNS service, and it has a highly available cell-based architecture with sharding and anycast. The routing between the 8 AWS regions is managed with the Route 53 routing algorithms. We have intelligence built to route to a different data center for any potential issues on the internet or our servers so that our applications continue to operate seamlessly. The next thing I want to discuss are the key drivers that help us accelerate the performance of our application. I spoke about how caching, if none match requests, byte range requests, all of those help us increase the availability of our application. It also goes hand in glove with improving the performance of our application. I highly recommend enabling TLS 1.3 with your web applications if you haven't already. Encrypted connections are faster with TLS 1.3 than 1.2. You need 2 round trips to complete a TLS handshake with TLS 1.2, while you only need 1 with TLS 1.3, thus cutting encryption latency in half. Another advantage of TLS 1.3 is that it remembers. On sites you have previously visited, you can now send data on the first message to the server. This is called 0 round trip. So that car that I was talking about, which lost connectivity as it went inside of a tunnel, it now sees improved load times as it reestablishes its connection on TLS 1.3 once it is outside of the tunnel. We at Mapbox are obsessed with providing the best possible experience to our customers, and this is why we look to reduce every millisecond that we can. TLS 1.3 is also more secure than TLS 1.2. TLS version 1.2 used ciphers with cryptographic weaknesses that had security vulnerabilities. All of them are removed in TLS 1.3. TLS 1.3 supports cipher sweeps that do not include key exchange and signature algorithms. GCM cipher modes are considered to be much more secure since they are not vulnerable to padding attacks. TLS 1.3 only supports GCM and other modern block cipher suites, making it more secure. It also removes the trouble of cipher suite ordering. The next thing I want to talk about is compressing your content using Brotli. The advantage for Brotli over gzip is that it makes use of a dictionary, and this only needs to send keys instead of full keywords. Since Brotli was designed to compress streams on the fly, it is faster at both compressing content on the server and decompressing in the browser than gzip. We are able to turn on Brotli with a click of a button on CloudFront, and the CDN is able to distinguish between the client who advertised support for Brotli or not, and serve Brotli or gzip accordingly. Your application code of the origin doesn't need to serve Brotli-enabled content to CloudFront if you want to do this, or if you don't want to. By enabling Brotli on our application, we saw an 8% reduction in bandwidth. Since the content we actually serve at Mapbox is mostly binaries, this is actually on the lower percentage side. But for a traditional web application, this would look even higher. Typically, you should expect to see gains of up to 25% over gzip compression. Similar to TLS and HTTP2 adoption, Brotli went through a gradual adoption across web platforms. Today, Brotli is supported by almost all web browsers globally. If you're hosting content yourself, your hosting infrastructure needs to have backwards compatibility to serve gzip compressed assets for older platforms which do not support the Brotli format, which can add complexity. Sagar is going to dive deep into this, but the use of serverless functions on CloudFront enables us to execute our code globally without having to provision our own servers or manage infrastructure. We're able to move our business logic to the edge, giving us the ability to deliver responses to our end customers. As customers rely on our web applications to fulfill their everyday needs, a business's success is directly proportional to its application's performance. It is critical for a business to deliver top-notch user experience, and we at Mapbox put a lot of effort into the application monitoring to make that happen. Let me show you how we do that. Mapbox processes over 20 terabytes of CloudFront log data each day through a system similar to what you're seeing right now. We have built dashboards powered by CloudFront logs, which are used for different use cases, ranging from our on-call engineers responding to alerts based on monitoring data, or the product and infrastructure teams doing trend analysis to derive product improvements, or to determine the best location for our next data center. So this is a dashboard that we look at to understand the most popular geolocations for a Mapbox location data set. We use this information to push targeted updates to those data products to further improve our end customers' experience. Our on-call engineers that I was talking about earlier would use this dashboard to get a view of latent requests. So we have the ability to drill down by edge locations or country and so on with this particular dashboard. The circle size increases with the volume of the end user's request. This is probably our most powerful statistic. Availability is the measure of how available your application is. That car driving through a tunnel that I was talking about earlier, do they enjoy an uninterrupted experience? Well, that's what we strive for. When we measure availability, we also discount the slow requests even if they were successful, because that is not the experience we would like to give to our end customers. When we measure availability, so the x-axis here is time. The y-axis is availability percentage. The dotted red line is where we never want to be. But when we hit that red line, it does set off an alarm in real time, and our incident response kicks in. All of this monitoring that I've shown is powered by CloudFront Access logs. In October of this year, Amazon CloudFront added 3 additional data fields in CloudFront real-time logs. With these 3 new data fields, we can now get more granular insights on CloudFront performance while analyzing real-time logs or in the dashboards created using the logs. So you get to see origin first byte latency, origin last byte latency, autonomous system number, which identifies the network, such as the ISP or the client IP making the request. These are very valuable data points from a performance monitoring standpoint. As you see, Mapbox has built infrastructure that constantly monitors, analyzes, and processes data from CloudFront logs in AWS. When you're monitoring your traffic on CloudFront, I recommend focusing in 4 areas. First off is ensuring that you maintain a high cache hit ratio, as this is an important metric. Actively monitoring this across the site or certain directory paths helps you identify opportunities for improvement and also potentially discover regressions. If a recent code release busted cache for a specific directory on your website, you would know. Latency is a very common thing to monitor, but how you measure and monitor it is critical to getting the most information from it. I would suggest that you monitor P99, P90, and P50 latencies regularly and monitor the patterns in them over an extended period of time. This is an excellent way to quickly narrow down where issues lie within your service. We all want to ensure that our customers are having an uninterrupted experience on our application. Monitor the errors both at the edge and the origin to help narrow down where the issues lie. If CloudFront times out waiting for a response from your load balancer, this can result in an error for your customer. Lastly, baseline the traffic levels on your application. Know what the traffic patterns look like. Set up alerts accordingly, but do not be married to having a static alert threshold. As an example, if you're an e-commerce customer, your usual traffic patterns are going to be very different from the peaks that you'd experience during a Black Friday sale. Also, regularly fine-tune your alert thresholds. If a real alert gets lost in the noise, it may not get actioned upon. With all of the work that we do at Mapbox to continually improve the performance of our application, we have seen more than 90% of our total bandwidth offloaded on CloudFront. This is a staggering statistic because it means that only less than 10% of our global traffic reaches our application servers. We are very excited to continue building our application with Amazon CloudFront. And now, with that, I'll hand it back to Sarah.
Thanks, Blake. So as we look to deliver more personalized experiences to the end user, there's a growing need to process the data at a very low latency. One of the key features of CloudFront that Mapbox uses is a serverless compute environment. And I'll discuss some of the architectural details and benefits with you all. So in general, there are obvious benefits to serverless computing. You don't have to pre-allocate server resources. Your spend is just optimized. The devs can focus on writing the code, building applications, and businesses can push out new features quicker and stand out in an increasingly competitive technological landscape. And all of this is great, but sometimes you could face some of these challenges, like cold start, regional latency, and lack of control. And as you look into each of these, cold start exists in serverless domains, just like you see bicycle accidents on the streets. As worrisome as these accidents might be, they can be avoided with a little defensive driving. With Amazon CloudFront, our platform does the heavy lifting to ensure that we mitigate some of these common challenges that you would otherwise face. You may have heard Peter DeSantis speak at length in last night's keynote on this and some of the exciting work that we're doing in this space. Regional latency is another cause of unpredictability. Given the massive scale of Amazon CloudFront, we are able to execute your code across different edge locations simultaneously rather than running from one centralized location. And the third is lack of control. So in other words, you don't have control over the entirety of your software stack. So this could lead to losing control over the configuration you want, loss of control over benchmarking performance on what to expect, and the security of the application that you would build on these environments. But if you're building on AWS, I spoke at length earlier on how we've built a reliable and secure infrastructure without trading off performance. So let us manage the infrastructure for you while you can focus on writing the code. With the serverless functions on CloudFront, you can write the code to manipulate the requests and responses that flow through CloudFront, perform authentication and authorization, generate HTTP responses at the edge, and more. In this section, I will be primarily focused on CloudFront functions, where you can build lightweight functions in JavaScript and run them at our 450+ edge locations. Lambda Edge has been around for years, and I'm sure almost all of you use it. It runs your complex compute-heavy use cases in a Node.js or Python runtime environment. Mapbox uses Lambda Edge to convert data format of certain files before they deliver it to their customers. The origin code base today creates the file in a single format, and they use the origin response trigger with Lambda Edge to do the conversion without having to write the additional code and maintain the same file of two different formats at the origin. And this solution was simple to implement and 15% faster than the alternative implementation that they had at the time. It also saved Mapbox about 30% of the cost by moving the logic to Lambda Edge. CloudFront Functions is purpose-built to give flexibility of a full programming environment with the performance, scale, and cost effectiveness that modern web applications require. CloudFront Functions executes JavaScript code natively at CloudFront's edge locations and scales instantly to millions of requests per second so that our customers do not have to worry about burst or throttling limits. We recommend that you use them for high-scale, latency-sensitive CDN customizations. So when we were architecting CloudFront Functions, our goal was to deliver a high-density code execution environment which would deliver tens of millions of requests at sub-millisecond latency. CloudFront Functions is built for these use cases, which require a small amount of compute before a request is served by the CloudFront's edge locations or right before you deliver a response to the end users. With every service that we have built, we've prioritized security over everything else. When CloudFront Functions was launched, it was no different. I want to walk you through its architecture today. So here you see that the end user makes a request, the request comes to the edge server, and the TCP connection is terminated. Here, the edge server then loads the distribution config to understand the rules that need to be applied to the request. It'll then check to see if there's a CloudFront Functions request associated with the distribution or not. So the process basically makes a call to check, like, hey, do I have a worker for this function? Do I not? And if it does not, then it'll have a worker, and it'll associate that new worker to the distribution. As the worker is associated, the CloudFront Functions pulls the customer code while it remains encrypted. We use process-based isolation to build an execution jail to run the customer code in it. The runtime that we use ensures that we are not vulnerable, even if the JavaScript engine has a vulnerability, and such a vulnerability could not be exploited to actually execute code. We also significantly lock down the number of system calls that CloudFront Functions processes have access to. So none of these system calls can open files or sockets or devices. They cannot establish network connections or otherwise communicate with anything other than the CloudFront component that sends the HTTP events and receives the function's responses. We also isolate a set of CPU cores on the servers and exclusively dedicate them to run CloudFront Functions. By running the customer code in isolated CPUs, we guarantee a complete level of isolation between the customer-supplied code and the entities managed by CloudFront, such as the data flowing through the customer distribution. We also disable simultaneous multi-threading, and all the CPU state is flushed when switching between functions. Also, CloudFront Functions does not have access to any timing functionality whatsoever, so they're not allowed to create threads, which could be used to create a makeshift clock. And these mitigations protect us against potential future side channel attacks. Since CloudFront Functions was launched, we've received overwhelmingly positive responses from our customers. We do trillions of executions in a month on CloudFront Functions on the AWS platform. We have seen customers use it at scale by doing more than 1 million requests per second on a per distribution basis. So to summarize, Lambda at Edge is a good fit if the function takes several milliseconds or more to complete. It requires adjustable CPU or memory, depends on third-party libraries. It requires network access to use external services for processing, or requires file system access or access to the body of HTTP requests. Waiting room is an excellent use case for Lambda at Edge. So sudden increase in the traffic can overwhelm your applications and infrastructure, leading to slow performance or complete disruption of your online presence. By building the waiting room solution using Lambda at Edge, you can send the excess traffic to your waiting room page, keeping users sticky to the branded experience and protecting the origin from being overloaded. So like your checkout pages, shopping carts, subscription services, donation pages, registration forms, they will all benefit from implementing the waiting room solution. CloudFront Functions, on the other hand, are best for use cases like cache key normalization, header manipulation, URL rewrites, URL redirects, request authorization, etc. So as an example, using CloudFront Functions, you can easily manage and offload high volume of URL redirects to the edge, providing operational simplicity, improved performance, and origin offload. All those redirects that come from your marketing and branding teams or are related to site migrations, they can all be offloaded to CloudFront Functions. The CloudFront distribution will call the CloudFront function, which will find the matching rule and serve the response downstream to the client. And all of this also applies to the URL redirects, which are typically running on a load balancer at the origin. And all those rules can be offloaded to the edge, making it easier to manage and to scale. So building on the success that Mapbox has had integrating CloudFront into the application, we are working with Mapbox as they explore adding in some of the latest CloudFront features that we've launched this year. So I'll first talk about server timing headers. Server processing time can be a significant fraction of the total request time. For example, a dynamic response may require the backend to run one or more database queries, do cache lookups, make API calls. It also requires time to process that relevant data and then render the response back to the end user. Similarly, even a static response can be delayed due to overloaded servers, slow caches, or transient issues on the network. Today, the user agent developer tools are able to show when the request was initiated, when the first and last bytes of the response were received. But there's no visibility into where or how the time was spent on the server, which means that the developer is unable to figure out or quickly diagnose if there's a performance bottleneck on the server. And to answer this question, the developer is required to use different techniques, like look at server logs, embed performance data within the response, or rely on external tools. This makes identifying and diagnosing performance bottlenecks difficult. Server timing defines a standard mechanism that enables the server to communicate relevant performance metrics to the client and allows the client to surface them directly in the developer tools. For example, the request can be annotated with the server sent matrix to provide insight into where or how the time was spent while generating the response. As you see in the image, all the modern browsers support server timing headers today. The numbers in the green are version numbers of the browsers that support server timing headers, while the red box represents those browsers that lack support as of now. The job of server timing is not to help you time activity on your server. You're going to need to do that yourself with whatever toolset your backend platform makes available to you. The purpose of server timing is to specify how those measurements can be communicated to the browser. So this is an example of a server timing header that a developer who's running some tests will receive from Amazon CloudFront when the server timing header setting is enabled. So as you look through this example, it says, we see that it took 30 milliseconds for CloudFront to complete the TCP connection to the origin. It tells me here that the requested object was not in the CloudFront cache, and the request was received by the edge location identified by the code PHX50C2. That's the unique request ID for your log pools. And we see that it took 436 milliseconds for CloudFront to send the first byte of the response to the end user after receiving the request. The next thing that I want to talk about is the JA3 fingerprinting on CloudFront. So fingerprinting clients and blocking them based on a particular set of rules is not new. Earlier, many websites used to fingerprint clients based on user agents. In today's world, it'll take seconds to impersonate that. As cyber criminals become more adept at using encrypted data against targets, fingerprinting techniques can help detect and prevent attacks from succeeding. JA3 fingerprinting uses data exchanged between a client and a server during an encrypted session to create signatures. The signature can be compared to the expected value for a given application or to known signatures of hackers, providing an efficient solution to thwart attacks. But the big question is, why do we care? So if you look at this pyramid bottom up, it tells us that it is relatively easier for the threat actor to change the hash of the attack tool or use a different IP address or a domain and continue with the attack in an attempt to outsmart you. But it gets difficult for the malicious actor to make changes as you go up the pyramid. And as you encrypt the traffic, it further obscures the activity. And hence, we need to shift the focus to the top of the pyramid. So once you get into the client applications and the tools that they use, it is difficult to change that. And that is why we focus a lot on identifying the tools. JA3 sits at the tools layer, and you map the JA3 fingerprints to the client applications. And how does it work? So to initiate an SSL connection, a client will send a client hello packet following the TCP three-way handshake. The packet and the way in which it is generated is dependent on the packages and the methods used when building the client application. The servers will respond with a server hello packet that is formulated based on server-side libraries, configurations, and the details in the client hello. Now, because SSL negotiations are transmitted in the clear, it is possible to fingerprint and identify client applications using the details in the client hello packet. So JA3 gathers the decimal values of the bytes from the fields, like it looks at TLS version, TLS extension length, cipher suites, elliptical curve groups, elliptical curve point formats. And these strings are then MD5 hashed to produce an easily consumable and shareable 32-character fingerprint. And that is the JA3 SSL client fingerprint. With the JA3 fingerprints in hand, the detection systems can get to work. Threat detection tools can compare the JA3 fingerprints to the expected fingerprint for a given encrypted application, and also to known fingerprints of malicious hackers. Some of the exciting applications of this are you can redirect endpoint-specific traffic based on the JA3 fingerprint and also allow particular JA3 fingerprints. You can identify potential bot requests. You can track down and block malicious malware. With Amazon CloudFront, we now give our customers the ability to configure their distribution to forward the JA3 fingerprint information and header order information to the origin. In the CloudFront distribution, you will need to allow list these headers in the origin request policy. So the next that I want to talk about is testing the CDN changes in the dev environment, or CDN's non-production network, does not always uncover issues that you might see in production. Our customers requested us to build a blue-green environment on CloudFront, which will let our customers gradually ramp up their traffic to the new CDN code and quickly roll back if needed, thus greatly reducing the risks of CDN code deployment. I'm very happy to share that just last week, AWS announced the launch of continuous deployment support for Amazon CloudFront. So with the CloudFront deployment feature, you can choose to send a small portion of the production traffic to the new CDN code before deploying those changes to all the edge locations. CloudFront function will now allow you to create a second distribution which has your new application code. You can first test internally using the header-based or through viewer IP-based policy, and then set weights to divide the traffic split that you want to send to the second distribution, which has your new application code. CloudFront will manage the traffic split and provide associated analytics to let you decide whether you want to continue with the deployment or to roll back. Once the tests with the new distributions have been validated, customers can then merge the code back to the main distribution and cut over 100% traffic to it. And these are all the changes that you can make in the CloudFront distribution with this launch, like changing the TTL rules, cache keys, customizing error responses, making origin-related changes in the distribution, testing the Lambda at edge and CloudFront function with the new distribution code versus old, and adding geo restrictions in your CloudFront distribution. You can create this setup in minutes by using SDK, CLI, AWS console, and CloudFormation. To the clone distribution, you just have to apply the desired changes and then set the policy to be like weight-based, header-based, viewer IP-based to dial up the traffic to this distribution incrementally. And once the tests have been validated, you can copy the changes to the main distribution. With this setup, you're now able to better test your changes before the 100% global rollout of the code. You're truly able to push out code at a high velocity and have greater control over your software delivery. So the specs for HTTP 3 were finalized in June 2022, a few months back. While HTTP 2 introduced various improvements over HTTP 1.1, there remain further challenges and opportunity for the protocol. HTTP 3 aims to improve upon the shortcomings of HTTP 2, and to do that, it is built on top of QUIC protocol, which is QUIC UDP Internet Connections Protocol. So I won't get into the historical context, but with HTTP 3, there are protocol changes at the lower level from TCP to UDP. The stream and the flow control functions are moved to the QUIC protocol. QUIC addresses TCP head-of-the-line blocking by implementing reliable packet delivery on top of UDP at a per stream granularity. The aim of HTTP 3 is to provide fast, reliable, and secure web connections across all forms of devices by resolving transport-related issues of HTTP 2. Since HTTP 3 runs on UDP, the handshake happens much quicker. If a packet gets dropped, it only interrupts that one stream and not all of them. It has much better error handling. Error correction is used to minimize retransmitting if the lost data, and it has a flexible congestion control. You're now able to enable HTTP 3 in Amazon CloudFront distributions. Amazon's HTTP 3 support provides enhanced security built on top of S2N-QUIC, which is an open source Rust implementation of the QUIC protocol added to our set of AWS encryption open source libraries, both with a strong emphasis on efficiency and performance. This past year has been an eventful year for the HTTP protocol, especially with the specs for H3 being standardized. We continue to observe high HTTP 2 utilization, but expect to see an increase in the customers now supporting HTTP 3. This is an exciting time going forward for the HTTP protocol and the web ecosystem. We are excited to see how these new technologies will get adopted and what effects they will have on user experience. So to recap, Blake and I spoke about how Amazon CloudFront plays an important role in accelerating Mapbox's applications. It's not just about making their maps faster and smoother. Mapbox is able to visualize streams of live data, like monitoring forest fires, running fast and accurate location services, and so much more. The strategic placements of the origins across 8+ AWS regions globally, powered with CloudFront, provides Mapbox with multi-site resilience with seamless failover and failback if there's a network event or an origin event. In the event of a service disruption, the traffic is automatically redirected using Route 53 to minimize the impact without the need for manual intervention. I have talked about many CloudFront features that we've launched in the recent months. Server timing headers and how they can be used by our performance engineering teams. CloudFront sending the JA3 fingerprint information to the origin, which your security team would appreciate. With the continuous deployment feature in CloudFront, it should significantly reduce the risk and minimize the downtime, which will bring some relief to your release engineering teams. With HTTP 3, you should all go back and evaluate your applications to enable HTTP 3 as soon as you can for faster speeds, reduced latency, and better handling of packet errors. I hope this helps you provide an even better experience for your customers. And yeah, that concludes our talk. So thank you very much for listening, and do not hesitate to reach out to us on Twitter. Blake and I will stick around for questions if you have any. Once again, thank you very much.